everyone can see those. Firstly, thank you very much for inviting me to come along and give a talk. This came about because I gave a talk in person at the London chapter meeting last December about the general history of the London Underground, and it was suggested I came back and did a sort of shorter version for Lunch and Learn. What I've done is I've actually brought it up to date a little bit with some of the more recent things that have happened around the underground as well, but also a bit more of a focus on some of the technology that's used for building the underground. The title of this is Building London's Tubes, so I'm using the word tube there accurately. London Underground has chosen to use the term tube in the sort of informal sense. They use the word to describe the entirety of the underground network, but technically speaking, the tubes are just the deep level lines that run in the circular tunnels that are bored out through mostly the London clay, as opposed to the subsurface lines, which are the Metropolitan, the District, the Circle and the Hammersmith and City, which to a large degree were excavated from the surface using the cut and cover technique. So rather than starting back at the end of the 1850s with the construction of the Metropolitan line, I'm starting mine round about the late 1880s, when the first part of the London Underground tube network was built. So in fact, the very first deep bored tube tunnel was made back in the late 1860s, and it was the Tower Subway, a very short tunnel which was excavated just upstream of where London Bridge is today, but Tower Bridge, but Tower Bridge wasn't there at the time. London Bridge was the most downstream of all of London's rivers, and so it was felt that having a way of getting people from one side to the other a little bit further downstream would be useful. And so an engineer called Peter Barlow came up with the idea of creating a tunnel that would cut through the clay and connecting with a shaft on both sides. It wasn't hugely successful. He had a very small railway carriage at the bottom which could hold 12 people, and it was pulled back and forth on a rope from one side to the other. Capacity was therefore very, very limited, and after not too long they removed the railway and they turned it into a pedestrian subway with staircases at each end to get down, still from before being used. Probably not a very nice experience. It was quite a narrow tunnel. The lighting in it was basically made by putting a metal pipe down the side of it, punching holes into it, pumping gas into it, and then just setting fire to the gas where it came out of the holes. So quite dangerous as well from a health and safety perspective. But the civil engineering success of building that led to a whole load of tube railways being promoted in the 1880s and 1890s. And I'm going to start off with a map showing by 1900 sort of what I've termed tubes to everywhere. So what you can see through here, we've got this solid line down the middle, which is labelled Central London. That was opened as a Central London Railway. It's now the Central Line, running from Shepherd's Bush in the west down to Bank in the east, with a dotted extension showing it to Liverpool Street. We've got a little bit here, which is the Waterloo and City, although it's written as City and Waterloo. We've got the section here from Clapham Common up to Moorgate Street, which is the City and South London Railway, or the Bank branch of the Northern Line today. Other than that, everything else is proposed in 1900. None of the other lines had opened. We've got the Brompton and Piccadilly, which is part of the Piccadilly Railway, the Piccadilly Tube these days. The Great Northern and Strand, which is the northern part of the Piccadilly line. We've got the Hampstead and Charing Cross line, which became joined up with the City and South London in the 1920s to become the West End branch and the northern branches of the Northern Line. We've got the Baker Street and Waterloo Railway, interestingly with a branch to Euston, which was never built. There's also the City and Brixton Railway, which was partly proposed to use a disused tunnel and partly a complete financial scam as well. And then the Great Northern City, which did become the Northern City line of the London Underground, but was then in 1975 closed and reopened as what's currently the Great Northern section of the Thames Link and Great Northern Railway. So that's the only tube railway built to mainline size. But how do they build all of these? Well, here is Peter Barlow on the left. Here's the engineer. He built Lambeth Suspension Bridge, which was the predecessor to the current Lambeth Bridge. And he built that by pressing a steel cylinder down into the clay vertically in order to make the pilings, the foundations for the piers that underpinned the bridge. And while he was doing this, he thought, if I push this big steel cylinder horizontally, I could make a tunnel through the clay and we could potentially run a railway through it. And his student, an enterprising chap called James Henry Greathead, the chap with the amazing beard on the right-hand side, worked with him, and together they built the Tower subway. The picture in the middle is a tunnelling shield. So this is the creation, their invention, which was used to actually make the tunnel. And it's really incredibly simple. So this is the end cross-section. So you can see part of that make a circular tunnel. This is the cross-section longitudinally. So basically, it's a steel cylinder which is shorter than it is in diameter. So if you imagine a tin can, like a food can, with the ends cut off, and actually probably one of those sort of half-size cans, that's what you've got there. Now, obviously, that would be really flexible and flimsy. So you have a steel partition that runs through the middle of it with a rectangular hole. So that gives it the rigidity to stay circular in cross-section. It's also got two what are labelled as hydraulic presses here. So the original one had screw jacks, but they then made them hydraulic presses, and hydraulic in the sense of water rather than oil that we would use today. One of the key bits you can see here is in the middle, it says end of completed tunnel, and you can see the tunnelling segments are slightly shaded. And the skin, the steel cylinder skin of the shield overlaps with those. And that's really important because basically it means there's never any exposed clay except at the very front where it's being excavated. The clay is always supported either by the steel cylinder of the tunnelling shield or by the completed tunnel lining. So what happens is miners reach through this rectangular partition and they just excavate the clay out in front. It's trimmed to size by these steel cutters to give it a neater edge, but that will give you a circular hole through it. Once you've excavated enough clay, you then activate the hydraulic presses, which press against the last piece of completed tunnel and push the tunnelling shield forward into the space that's been made in front of it. Those presses are then retracted and another ring of tunnel is created in the space behind it, within the shield, and it's bolted onto the last piece of tunnel. While that's going on, while one group of men are busy bolting those together, the tunnellers are busy excavating the clay from the front again. And this process carries on. A tunnel ring is typically about 18 inches wide. So effectively, you're moving the tunnel forward in 18-inch stages. So not fantastically fast, but a lot safer than trying to tunnel without being able to support the clay. So this is a modern illustration of how the City and South London Railway was built. So this is the first one. Built with James Henry Greathead as the engineer in charge. He started by building the under-river section, which seems like a slightly odd thing to do, but the critics at the time said they'd never be able to build the railway, or at least if they were, they'd never be able to build it for the price that they'd said. And so the bit that was felt to be most difficult was the under-river part. So Greathead felt that if he actually built the under-river tube first, that would silence his critics and he could then get on with building the easier parts underneath land at each end. It also had the advantage that he had no obvious site from where he could start tunnelling. London is really heavily built up. Buying land is really expensive. And in the city, the first station site, they used a building that was already there. They didn't want to demolish it, so they sank the shaft for the lifts within that building. But you obviously couldn't build the entire railway from there. So what they did is they built this great big pier and then staging out into the Thames, connected by that little footbridge that you can see. And from there, they sank a shaft down to the riverbed and then kept pushing that down by sending men into the shaft once the water was pumped out, excavating underneath and just dropping this effectively big steel cylinder into the Thames that slowly sank under its own weight until it reached the appropriate level. Once it was there, underneath it, where the two tunnels cross here, they built a great big block of brickwork that had four what are called tunnelling eyes, the parts where the tunnels would start. So one for each tunnel, one in each direction. Now, I've only said there's one shaft, there's two tunnels. So what you can see here is the two tunnels are directly one above each other here. So there's two reasons for that. One, it meant they could get away with just having a single shaft in the river. But two, to the right-hand side of this picture, the tunnels had come under land and the street there is very narrow. It's called Swan Lane. I think it's Old Swan Lane now. And the tunnels had to fit underneath the public part of the street, because if they passed underneath anyone's building, they would have to buy the building or negotiate the way leave to pass underneath it, which in those days there's no compulsory purchase. The only thing they could do without needing permission was to tunnel under the street line. So they could fit the two tunnels under the street if they were one above the other. So they built this block and they then started tunnelling out in both directions in both tunnels. So 4 tunnelling shields going at once, excavating to the north and the south side of the Thames. All the clay comes back up and then gets put straight into barges, such as the one you can see in the centre there, which means it can then be taken away really easily without having to take it away sort of one cartload at a time, being pulled by horses through the crowded streets of London. So yet another advantage in building from the Thames. Here's a really early photograph. This is the staging that was built for the Bakerloo line. So in the background, you've got the Hungerford River Bridge. That's leading out of Charing Cross railway station on the left of the screen, passing across to Waterloo on the right-hand side of the screen. You can see the staging there. In the background on the left, you can see a little white footbridge that's been built to let workers cross to the staging. From there, they actually sank two shafts down, one for the northbound tunnel and one for the southbound tunnel. There were cranes on board the staging. There were workshops on board. There were electricity generators because they used electrical lighting down in the tunnels. And there was even decompression chamber because they were using compressed air, and the miners that came up, if they started to suffer from the bends, medical staff, this was a brand new innovation at the time, medical staff on the staging could take the men, repressurize them, and then slowly take the pressure down for them to try and cure them of the bends. Also, real innovation at the time, they had dry clothing for the miners who came back out of the tunnels and hot coffee for them. So, yeah, an early example of actually trying to treat your staff nicely. Here's an illustration of what it was like in the tunnels. I think this one's in Bakerloo line again, underneath Regent Street. You can see the rectangular partition in the background. Just through there's a couple of men with pickaxes who are mining the clay. In the centre, there's a small wagon running on temporary narrow gauge track that all the clay is being loaded into. The man at the left in sort of pale coloured top, quite luxuriant white moustache and a cap, is busy controlling a grouting machine. So this used compressed air to force a liquid cement through holes in the cast iron lining segments to fill up the little tiny gap that remained between the clay and the segments, because the shield always excavates a slightly larger hole than the size of those cast iron segments. And so you fill that gap up with clay, with cement, grout, as fast as possible, because that way it stops or reduces the subsidence that will occur at the surface above the tunnel. What else can we see here? There's a couple of light bulbs. In fact, I think you can probably just about see three. There's one right at the top, there's one in the middle just below the curve of the tunnel, and there's possibly one that's visible through the partition. Next to the man operating the grouting machine, there's a candle. So this looks like quite a clear picture. I suspect it was rather darker for those people who were down there at the time. Still, a massive improvement over the city in South London, where the mining was done entirely by candlelight, with the miners using a blob of clay, sticking it to the peak of their cap and pushing a candle into it. So each man had one candle, which was very easy to blow out. Bit of technology here. This was used for the Central London Railway. This is a hydraulic segment erector. So each ring of tunnel was made up of between 6 and about 10 pieces of cast iron, depending on the size of the tunnel. They're really big. They weighed a couple of hundredweight each. And so manhandling them into position was fraught with difficulty and probably quite a lot of danger for people's fingers. So hydraulic segment erectors enabled them to bolt each individual segment onto a hydraulic arm that could then swivel and lift the piece in place and hold it still and in position while it was bolted into place. So you can see here the arm in the middle, there's two workers sitting on it, one worker behind, and they've got one large segment that looks like it's probably about to be positioned possibly to the right and slightly lower down the tunnel, or it may well be it's about to be swiveled up to the crown of the tunnel, which is the hardest place to place these. Quite a lot of clutter around in the tunnel as well. There's some wooden staging there that's being used to reach the top part of the tunnel, and there's some clay and possibly a wagon at the bottom as well. From the size of it, this is probably a platform tunnel. The platform tunnels were about 21 feet, 2.5 inches in diameter, unlike the running tunnels, which tended to be about 11 foot 8 up to 12 feet. So various experiments that were done in how to make the mining of these tunnels more efficient. So the water tank here is linked to a pump, and it sprays water at high pressure at the clay from the front end. If you see the pipes here, there's an arrow showing letter D here. This is going out to a series of water jets which were blasted at the clay in the hope that the high pressure water would break the clay apart and then wash it down to the bottom of the tunnel, where it would then be brought back in pipes around to the tank, where the lumps of clay would settle out and could be deposited into the two little wagons underneath, and the water with rather less clay in it could then be pumped back round for another circuit. This was used on the City and South London Railway. Aside from the mention of it being used, it never got mentioned again, so I suspect this was rather unsuccessful. Rather more successful was putting in place wooden wedges around the edges of the tunnelling shield, or even steel cutting plates. This just enabled to break the clay up. With each press of the hydraulics, it would break the clay up around the edge and make it that little bit easier for the miners to break the clay out. Within the tunnels, different experiments being made. So you can see here another temporary railway in the illustration on the left, and the innovation here, like we saw in the previous photograph, is the electric light being used to make it easier for people. On the right, with the Waterloo and City, left is showing, again, electric light bulbs. You can see a series of people mining. They're actually putting a wooden platform down the tunnel to give them a flat stage which they can work. The more interesting one here, actually, is the one on the right. This is the Waterloo and City Railway, today's Waterloo and City line. And you can see they put boards up around the edge of the tunnel, and they're busy shoveling. And what they're doing, they're shoveling concrete in to fill the inside of the cast iron lining. And they thought that if they gave it a completely smooth lining, then that would reduce the level of noise in the tunnel. It completely failed. It was a complete waste of time. It was probably horrendously difficult for them to get the concrete in, especially over the top of the tunnel. But nonetheless, this was a period where there was lots of experimentation going on to find the best way of building these railways. So this picture, I've deliberately used this one from this angle because it's got some track in it for you. This shows the Waterloo and City line that on a tunnel walk I did a few years ago, and you can see the concrete is still there. It's unlike all the other underground lines, the early ones anyway, in that it appears to be a completely smooth concrete bore. You can just about make out the pattern of the tunnel segments within it, but all of the other early underground railways are either lots and lots of cast iron segments, or more recently, concrete segments where you can see how clearly they've been bolted together. This is just almost smooth concrete throughout. So I mentioned the compressed air on the Bakerloo line. So this is a cross-section of the Bakerloo underneath the Thames, and you can see that there is a large dip in the gravel. So the clay is the dark shaded piece towards the bottom. This medium shaded bit that dips right down here is gravel, and gravel under a river is going to be full of water. And the only way they can make their tunnel go through was to go all the way through that gravel. So they needed a way of being able to hold the water back while they tunnelled that out. And what they did is they used this tunnelling shield that you can see here on the right that basically had an extra partition through it and a manhole. And so the men would actually have to climb in through the front, excavate out through sliding shutters. So one shutter would be removed at a time, remove the gravel as they went through, and then try and shovel that back round, and then close the shutter, push it forward into the space, and then start work on another one. And all of this is being done under compressed air. So some way behind this shield in the tunnel is what you can see in the photo on the left, a big airlock. So this is actually two airlocks, these two cylinders, one above the other. The bottom one's got tracks going into it so they could wheel materials through. Really important because obviously all those tunnel segments needed to go in and all the clay and gravel needed to come back out. So the railway continued through the airlock, and they can wheel all that stuff back and forth through it. The bench on the left is so that the men can wait their turn while the airlock is readied and the pressure is increased and decreased. But the main reason is to be able to keep constant air pressure at the front to hold the water back. Again, here's the staging in the Bakerloo line with the Hungerford Railway Bridge in the background. The clay is coming up the shaft, lifted up from buckets from the wagons underneath, like the City in South London, tipped straight into barges, and this was taken all the way down the Thames to a sandbank called the Nore, where it was just dumped. How did the men get in? Well, it was fairly crude. You have the buckets to bring the clay and materials up and down, so you use the buckets to make the men up. Take the men up and down. So this is an illustration from a newspaper in 1888 showing the City in South London and the navvy descending the shaft. You stood on the bucket, you held the rope. That was it. Obviously, rather different these days. I tried to have a look and see how did this change over time. The really scary thing is 1976, building the Jubilee line. This is the working site in Trafalgar Square. And we still have men standing in a bucket holding onto the rope being lowered down the tunnels. It was only once you got into the 1980s and 1990s that you started seeing, firstly, full personal protective equipment, but secondly, the introduction of proper sort of temporary works elevators to get people in and out of tunnels. health and safety was right the way through until about the 1970s. The photos just are quite scary compared to modern day tunnelling. This is a really, really rare photo that I found in the archives some time ago. This is part of the Northern Line being tunnelled in 1905. It's the only photo I've ever found that shows a pony being used. I've read about ponies being used right from the early days, but this is the first time I found the actual evidence of it. They would lower the ponies down into the tunnels to pull the trains of muck wagons out and the trains full of new segments back in, because they didn't have any other way of moving them in. Tunnelling was seen very much as a branch of mining, and so ponies were used in coal mines around the UK. Why wouldn't you use them for effectively a clay mine, where the objective is not to get the clay but to use the space afterwards? So yeah, it appears that they were used up until probably, I think this may well have been one of the last to have used ponies, but 1905, 1906 is probably the last use of ponies to excavate the underground. It's such an evocative picture with the sort of the lad in the foreground with his waistcoat and his flat cap and so on, who's obviously the chap who would lead the pony back and forth. No stabling underground, unlike in the coal mines, so the ponies would have had to be taken in and out of the mines, out of the tunnels every day, up and down the shafts. God knows what they thought of it. Other nice photos I found. This is a photo midway through constructing an underground station. So this is archway. You can see the two lift shafts in the ground. No safety fencing or anything around them. A couple of flimsy ladders leading up the framework. The steel framework there, made by Dorman Long and Co., the people who built the Newcastle Tyne Bridge and the Sydney Harbour Bridge. That framework is holding up the lift motors, so it's not actually structural for the building itself. More structural steel will go up around all of this to support the building, but this is just to hold the really heavy lift motors and all the equipment up at the first floor level directly above the lift shafts. This comes directly from the archives of the Otis Elevator Company. This is Earl's Court Station. That glazed train shed is still there above the District line. You can still see where the lifts are down to the Piccadilly line. And this must have been fascinating for the passengers getting their trains on their steam-hauled trains on the District line at the time, watching these motors being put in place. And in fact, the electrification of the District line was going on at the same time. So round about the point that this was going up, they would have a mix of electric and steam trains going through the platforms behind where the photographer's standing. So really interesting time to have been around on the underground. This is Marylebone Station, slightly unusual. It's a single-storey station. So most of the stations were 2 stories high with the lift machine room above on the first floor, because the ticket hall and the upper lift landings were at ground floor level. Marylebone, you probably can't quite see it, but the entranceway in the middle there is stairs going down. The ticket hall was at basement level, and so they put the lifts at ground floor level to save having to make the building bigger than necessary. And that's the lifts there with the pulley wheel for the cables in the photograph on the left. Another photo, that's what buildings looked like when they were completed. You still see quite a few of these. They're in a sort of dark oxblood red tiling. This is Hampstead Station on what's the Hampstead Tube, now part of the Northern Line. The only thing that's missing from this is where there are these grey stripes around it. That was tiled with a frieze, given the name of the station and the railway company. But this is obviously in the final days before it opens, because the building is practically complete and there are already posters outside advertising the line and the railway. So, showed the drawing earlier of the original Great Head Shield. Here's a model of it, which is currently in the London Transport Museum. So you can see around this, there are 6 hydraulic rams. The original shield had these hand pumped. So basically the men in the shield would have to operate pumps manually in order to pressurize the system and push the rams back. The exact pressure going through to each ram had to be carefully controlled. If they all had the same pressure going through them, then the shield would be pushed forward in a straight line. But if you put slightly more pressure, say on the right hand side here, the shield will start to steer to the left. And so part of the art of building one of these tunnels is being able to steer the shield precisely along the line that you've determined for the railway. And of course you're steering it in 2 different dimensions as well. As you're pushing it forwards, but you can steer it left and right and up and down, and the tunnels had to go up and down, both because stations tended to be built at a slightly higher level to give the trains a decelerating gradient into the platforms and an accelerating gradient away from the platforms. That also reduced the depth of the lift shafts that needed to be made, and therefore the time it would take for passengers to get to the platforms. So it had a number of advantages, but it did make constructing the tunnels slightly harder because of the up and down gradients that needed to be built. A chap called John Price, who was one of the contractors on the Central London Railway and then later on the Piccadilly line, looked at this and said, well, rather than just pushing this metal tube forward and having men using pickaxes, why don't we motorise it and make it so it actually scrapes the clay out for us? His first attempt didn't work very well, so it had a centrally driven axle that turned the front of the machine round with scrapers on it. The trouble is that this is pressed against the clay face, so whenever you try and steer the shield, the rotary part of it stayed in the original alignment, and so it made it almost unsteerable. He scrapped that idea and came back a few years later with a centrifugal drive. So effectively you had the motor driving the edge of the rotating part through gears and gear teeth on the edge all the way around the circumference of it. And that meant that it stayed in perfect alignment with the front of the shield as it was steered. And that led to some really good advances in how fast they could build these tunnels. The view on the right shows the back of it, so you can see where the hydraulic rams would be around it. You can see the motor along on the left, and just down here on the right is the chute that the clay would automatically be dropped down. So on the left, you've got these scoops that will shift the broken clay, and as the wheel rotates, drop it into the chute there. So you could have a wagon underneath that would collect the clay, or even just a wheelbarrow, and take that away for disposal. In the 1960s, drum diggers came about. So these were developed by Sir Robert McAlpine and Kinnair Moody independently. So they came up with two different forms of drum diggers. This is basically a really large rotating drum with cutters and with a lot of equipment at the back that can move the clay, support all the grouting equipment, and also support the tunnel segments while they're being erected. So again, another advance in how fast the tunnels could be built. These were akin to the tunnel boring machines. This is almost like the grandfather of the tunnel boring machine, as it were. The other advantage here is that you can see the man wouldn't be able to stand there if they were tunnelling, but someone could get through to the front and replace the picks, the bits of the tunnelling machine which scrape out the clay, because they do wear out, particularly if they're lumps of rock. The TBM's ancestor came about from building a prototype tunnel that was going to be used for the Fleet line, which was going to originally be part of the Jubilee line. Fleet line was the original name for the Jubilee line. It was going to take over part of the East London line, which is single track. And so you can see here, we have a surface line that runs down to the northbound platform and a tunnel line. This really odd bit of the underground where in one direction trains are in a tube tunnel and the other direction they'd be running at the surface. The tunnel, part of the tunnel was actually built, and it was built by this, which is the proper ancestor of the tunnel boring machine. This was developed by the UK government and London Transport at the time, and was really successful in cutting through some quite complicated ground. So one of the main reasons for using a tunnel boring machine is that rather than just cutting through clay, they can cut through wet, gravelly and rocky soils. And this could support that using a thick clay called bentonite, which supported the front of the machine and the clay face without needing compressed air for the workers. Unfortunately, having developed all of this, Britain didn't bother capitalising on it and left it for the Japanese, the Americans, the French and the Germans to actually create the proper tunnel boring machine technology. So, for example, Jubilee line extension, seen here at North Greenwich, this is a tunnel boring machine made, I think, by the American Lovat company. The cutting end of it is being lowered in. That's the piece with the underground roundel on it. At the bottom is the motor, and the thinner part of that at the top, just a bit here, will plug into a hole on here. This is basically, it's a fairly constrained site, as you can see from these big steel piling tubes across it, and so they had to lower the TBM into the hole piece by piece and then assemble it at the bottom. The latest TBMs were used for building things like the Elizabeth line, which was obviously built as Crossrail. This is a picture of one of the ones made by the German firm of Herrenknecht, which made all of the ones used for the Elizabeth line. You can see the tunnel lining here. As with all of the previous tunnelling machines, the skin of the TBM wraps around it to ensure there's no exposed clay. We have the hydraulic rams around it in the middle. The large angled Archimedean screw running up pumps the spoil from the front chamber, I think it's what's called a plenum chamber, through to the back. So what happens here is the cutting end, the green part of it, rotates, grinds the clay and anything else that's quite large up, mixes it in with this thick bentonite slurry clay. All the heavy bits of it drop down to the bottom and it gets pumped out through this Archimedean screw, taken out to the back, sent off to a machine that will separate out the clay from the bentonite. The bentonite is cleaned and pumped back to the front, and all of the bits of chalk, flint, and other lumps of spoil clay then get separated out and sent off for disposal. But the idea is you never need to put people into here. This end is entirely autonomous and remains pressurized to support the front end of it. So that takes us up to the modern day for how we've been constructing tunnels on the underground and through London, or the tube tunnels. Obviously, some of the most recent tunnels were built for the Northern Line extension to Battersea, which used a similar machine to the Heron Connect, but of a French build. And there's a new section of running tunnel built at Bank as well, although because of the length of that was cut out using basic excavators rather than needing a tunnel boring machine because of the complexity of it. I'm pretty much bang on time, having taken about 40 minutes to talk to you. I wanted to make sure I've left time at the end for some questions. But anyone who has found this interesting and wants to know a bit more about how the tubes were built, I have a book that's actually been published just this week by Capital Transport, with lots more pictures, lots more explanation about how all of this technology works and how the underground was constructed, basically from about late 1880s all the way through to the most modern extensions. But with that, very happy to take any questions. Thank you very much.
Well, thanks, Tony. I see that everyone's already expressing their thanks in the usual way. That's great. We've had a couple of questions in the chat whilst you've been talking. There's been a shout out to the Health and Safety at Work Act, of course, in 1974, which was a turning point for health and safety for the whole sector, the whole industry. And we're very grateful to the authors of the 74 Act for improving the quality of working conditions for us all. But there's also a point in the chat there about the smooth concrete lining, which has appeared in some of your slides, which I suspect was partly to improve the acoustics, partly to strengthen the walls of the tunnels, or maybe to affect also drainage there. And it may also have had some impact on aerodynamics, but I suspect that with the speed of the tube trains, the change on the aerodynamics in the tunnels might have been fairly light. But if you've got any comments on that, Tony, then you're welcome.
So, yeah, I mean, the primary reason given in the press at the time was around seeing if they could bring the noise down. There probably was a little bit around the ventilation and the air, although given that the trains at the time were, like modern underground trains, pretty much flat-fronted and pushing the air through, in effect, they were making the tunnel slightly narrower by putting the lining in. And so they're probably increasing the resistance by making that tunnel slightly smaller there. It wasn't really, so in terms of tunnel strength, though, the cast iron was seen as being solid enough because all of the other railways were built without needing to put the concrete in. There's an interesting point that the tunnels for the platforms on the original City and South London were built out of brick rather than cast iron, because back in the 1880s, when those were built, there was a lack of confidence in the strength of cast iron to support the tunnels, and they decided that it was easier to build a larger tunnel that wasn't entirely circular to avoid having to build a huge void underneath the tracks, make it flatter at the tunnel invert, and build the whole thing out of about 5 rings of brickwork. Now, of course, the brickwork took longer to erect and did cause more subsidence over the station sites than having put a cast iron lining in, and that's the only time that was ever used as an approach with the tunnels.
That's interesting. Yes, that's interesting. I suspect that the economics of the steel industry and the relative cost of brickwork would have had something to play in that decision as well. Yes, yes. So we've got interesting questions in the chat coming through, and by all means, anybody on the call wants to add a question, please go ahead. We've got about 20 minutes before the scheduled end of this call. So, a quick question from Nick Smith. What's your favourite tunnel?
What's my favourite tunnel?
Yes.
That's a fascinating question.
That's a great question.
In some ways, that they all look pretty much the same. So it would be difficult to have a favourite tunnel. In terms of the one that I know an awful lot about is the Holborn to Aldwych branch. I wrote a book about that many years ago. I got fascinated with it as a teenager, having ridden on this bizarre little stub on the underground. and researched it and found it had an absolutely fascinating history. So I'd probably say that, and partly because it's disused and therefore more interesting in that regard, but also because of the amount of history it has there.
And Holborn Aldwych, if I remember rightly, you were saying earlier that was something that was rubber tired, or you mentioned that just before the call started.
That's right. So back in the because it was 2 tunnels, one of which had been disused since 1912, and the other one was still in use as a shuttle. It wasn't massively used. It was often used for doing experimental work. And so in the 1950s, after the Paris Metro started experimenting with rubber-tired trains, the Underground considered converting it to use rubber-tired trains of its own, just to see whether that was a feasible concept in a deep tube tunnel. That never went anywhere, sadly. That would have been fascinating to have seen.
Interesting. Thanks. And then another question. Sorry, go ahead, Tony.
I was going to say, before the favourite tunnel, there's a question about how was the line and level controlled.
Yes.
Theodolite and target plate, yes, as Michael suggested there, it was largely using a theodolite along the surface to actually work out the horizontal alignment of the tunnels. So going on the streets at night and then working out each line segment in turn, putting brass pegs into the pavement and working out all of the angles, and then working out all the heights cross-sectionally. Within the tunnels themselves, they would actually use rulers that were scaled for the radius of the curve that was needed. So if you were going around a particular radius curve, you would dig out the rulers for the left-hand and right-hand side, and so you'd measure off the same distance or the same markings on each ruler, but the ruler for the right-hand side, for the left-hand curve, would obviously be longer and have larger increments on it. So as long as you kept yourself on to exactly the same markings, you'd actually find you'd be going round a corner. They would also hang pieces of wood from the roof to get an alignment through that the theodolite could be used as a sort of target. It was very crude. These days it's all done using lasers and is far more sophisticated. That's probably another talk in and of itself, just about how they do all of that kind of calculation.
Very interesting. Yes, very interesting. So are there any particular ideas that you feel have been abandoned that you feel we should be bringing back? I appreciate that's probably a slightly unfair question since you're not a tunneling engineer, but from your experience of reading the history of these tunnels and these techniques, anything that you think we could add to our list of tunneling innovations for the 21st century?
Yeah, it's quite a difficult one to answer that one. I don't think there's been any good ideas that have been scrapped. The whole history of it is one of innovation, and every innovation is sort of building on what came previously. So we've moved from pushing a really simple steel cylinder through the earth to something that is now motorized, carries a canteen, toilets, other welfare facilities on board, has a computer to help drive it, uses lasers to almost like an underground sat nav, builds the tunnel automatically behind using vacuum segment erectors, is followed by a machine that drills all the holes in the wall and puts the cable brackets on. So I don't think there's anything abandoned that we should bring back. Obviously, fantastic advances in health and safety, which makes it so much better for the people who actually have to go and build these. And yeah, it's just become faster and faster to build these tunnels as well. So yeah, probably nothing I can think of off the top of my head. Unless there's a different implication behind the question. So feel free, if I haven't interpreted the question correctly, I think that's from Stuart Corrie, feel free to put a new question in. Sure.
No, I think that's what strikes me particularly is the old expression that necessity is the mother of invention, and what you've got is a period of fabulous investment in the Underground Railway, and companies and people are effectively falling over themselves to find different innovative ways of achieving their objectives, and that sort of intensity, the passion that goes into finding different solutions really comes across in the history that you've revealed to us there. Yep. So thanks for that. I mean, I think it's interesting that techniques are changing all the time. There's another question in the chat about the use of precast concrete, for example. Yep. And is there a particular time in your mind where precast concrete starts to come into the?
Absolutely.
Yeah.
About the just after the mid-1930s, they started experimenting. They made they built a tunnel underneath the very, very short piece of tunnel underneath the Central Line depot in Wood Lane. There's a photo of it, not of the tunnel itself, but of the ground above it. It's absolutely heaped with cast iron segments above it because they're trying to stress the tunnel. So it's not deep underground with a lot of clay to help absorb the forces around it. They've deliberately put it a short distance underground, and they're putting a massive load of iron on top of it to see whether the concrete segments will be damaged or not. And there's a really good reason for why the late 1930s are when precast concrete came in. And that's because there was an increasing diversion of Britain's iron and steel needs into rearming. So everything they could throw at building, particularly big ships, was being used there. And so they were looking around for anything that could be used for as an alternative. And so the first big tunnels that were built using precast concrete were the Central Line extensions out from Liverpool Street towards Epping.
In the 30s.
Also, 1930s.
Yeah.
So those tunnels were built round about the late 1930s because some of those were used as shelters and even a tunnel factory during the Second World War.
Interesting. There's some interesting questions coming through in the chat, actually, and some interesting elements coming there. There's one in relation to cast iron and the risk of catastrophic failure for cast iron. And there's a second part of that which relates to design life, but just concentrating on the cast iron aspect of that. Are you aware of any particular catastrophic failures associated with cast iron?
So there's never been any catastrophic failures because the tunnels are monitored and inspected on a very regular basis. There have been there's been primarily two key places where they've had a problem, and it's been the same problem in both. So most recently it was on the southbound Jubilee line between Baker Street and Bond Street. In actual fact, no, there's only one. The Baker Street and Bond Street one is a concrete tunnel that had the same problem. The cast iron one was up near Old Street Station. So the clay up there is slightly odd. It has lenses of sand in it. So if you tunnel through, every so often you'll find it's a patch of sand, and the sand contains iron pyrite, which is absolutely fine normally. As soon as you cut a tunnel through, you're adding oxygen to the mix and water gets into it. And the iron pyrite will oxidize to form sulfuric acid. So you now have a nice cast iron tunnel with a load of sulfuric acid piling up behind it. And that tunnel was built in about 1901, maybe slightly, no, it was 1901, it was the Angel extension. By 1945, they had noticed odd leaks coming through from between the tunnelling segments and checked them out and discovered they were highly acidic, and so started to investigate what was going on. They found the tunnel segments were starting to crack in places due to thinning because of the corrosion that was occurring behind. Various experiments were done, so they tried drilling a hole for the tunnel and seeing if you can pump in some alkali to neutralise it, and that failed. They realised that it was actually a really substantial amount of sulfuric acid, so they sank a borehole from the surface and pumped in large amounts of sodium hydroxide, which also failed. So they ended up putting a whole load of strapping around the tunnel just to ensure that it wasn't going to have a catastrophic failure. And then in the mid-1990s realised that the problem needed to be faced square on. So they ended up having to sink a new tunnel from a schoolyard off the site of the main running tunnels, underneath the running tunnels, and then up into a disused tunnel that was between it. It was an old siding that was between the two running tunnels, break out from that into the damaged areas of tunnel, and build a new tunnelling shield, which was large enough to encompass the old tunnel, but also to let trains run through the middle of it. So during the day, the train service could carry on, but at night, they would slowly dismantle the damaged tunnel, bore out an even larger tunnel that remained, and then they erected a stainless steel tunnel lining. It was the largest ever order by weight of stainless steel at the time.
Right.
And they rebuilt the whole tunnel in stainless steel to basically make sure that it's acid proof.
That's a really interesting story. Can you just remind us which tunnel, which section that was?
Yeah, it's just south of Old Street Station on the Northern Line.
That's really interesting. I've never heard that before, and a very interesting crossover as well between civil engineering and chemistry, which I'm sure people will have rushing to Google their chemical compounds and formulae. That was really interesting.
Yep.
Yeah.
In terms of design life, these days the tunnels are designed with a nominal 120-year design life minimum. Back when they were constructed, I don't think anyone really thought about a design life as such. That said, when they've taken tunnelling segments out from existing tunnels that aren't backed by sulfuric acid, so for example, where they broke the Bakerloo line extension, sorry, the Battersea extension of the Northern Line at Kennington to join to the existing tunnel. They had to remove a section of existing tunnel lining that had been put in the early 1920s, and the cast iron segments were immaculate.
Interesting. Yes, I think the concept of design life is something which is a relatively modern one, but people, it's one of those things as well where it's difficult to know whether you've achieved, of course, your design life.
Yes.
But there are some interesting questions coming through about clay and clay movement over time, but also the ability of clay to retain heat after. Presumably, that question's aimed at the clay's ability to retain heat after the disturbance of the clay. I'm not sufficiently specialist to be able to comment on that myself. Have you got any view on that,
Yep.
Tony?
So when the underground was built, the clay was pretty cool. I mean, this is the ground tends to be pretty cool. This is you know, what you'll find if you dig down deep enough, it tends to be fairly stable in temperature. And for many years, the underground advertised itself in the summer as being the coolest place to go, which seems laughable to us these days. And what's happened is slowly the heat has been absorbed by the clay, and it's acting like a giant heat storage bank around the tunnels. Not helped by the fact that every single person is acting like giving out the same heat as a 100-watt incandescent light bulb down in the tunnels. Plus, you've got all the electricity being used for the motors and so on. And so the clay does warm up quite rapidly. Oddly, the Victoria line, which is one of the newer lines, is one of the hottest lines now. And it seems odd until you realise that when the original trains were made, rather than using friction brake blocks to slow them down, instead they ran the motors as dynamos, like modern trains, but rather than regenerating the power and putting it into the rails, they just ran it through resistor grids to burn it off as heat. So they actually deliberately dumped even more heat than necessary into the tunnels on the Victoria line, where they were running an incredibly intensive service. And that's heated the Victoria line up to a greater extent than other lines. The one advantage it does have is that being more modern, it has a lot more ventilation shafts between stations. And there's been a programme over the last 10 years or so to refit all of those with higher capacity fans, because they've recognised that the tunnels are just getting too hot down there.
And the question of movement of clay over time is an interesting one as well. I mean, there's obviously a level of settlement associated with the tunnelling activity, and the grouting was something you mentioned earlier on. But do you think that I'm not aware of whether or not this settlement ongoing associated with tunnels through clay, other than that settlement at the Crown, is that something you've heard of?
No, so the tunnels themselves stay pretty static once they're in the clay. The settlement that occurs above while they're being built is now controlled in a very sophisticated way by computer-controlled grouting arrays, which are generally tunneled. They sink a very thin shaft down above where the tunnels are going to be built, and they can then control which direction the grout is injected in a layer, so that as the ground immediately above the tunnel crown starts to settle, they'll inject a layer of grout in to keep the ground above that at a fixed height. In theory, you can get places where you get isostatic uplift of the tunnels. So, for example, when Canary Wharf station was built on the Jubilee line, so that's built as a huge open box sunk into the ground, and because London has less industry than it used to, the water table has risen. So Canary Wharf station and many others are actually below the water table now. So when you build that box, if you imagine taking a large metal tin, for example, and pushing it down into a bath, you get a huge amount of buoyancy from it. And there is, I think the figure was something like 250,000 tons of vertical buoyancy trying to lift Canary Wharf station up, that huge concrete box that the station sits in. And so the box itself is anchored into position by a huge number of piles that are sunk deep underneath to lock it into the ground, so the water doesn't try and make it bob up, because that would be rather disastrous.
We're going to be quite short of time now, Tony. I'm keen to finish because people have jobs to go to and so on at 5:30. But there've been a couple of other questions which I'd like to try and cover very briefly, if that's all right.
Yep.
How would any southbound extension of the Bakerloo line, which is obviously bored through gravel, south of the Thames, be bored? I think there's probably some examples we could identify of boring through gravel, which would point to an answer to that question. Is there anything that comes to your mind?
Yeah, very similar to building any of the other tunnels through South London. So they'd use an earth pressure balance tunnel boring machine, which is designed to hold it all back using the bentonite clay, like I showed with the picture of the Heron Knecht shield.
Yes, and to what extent is British engineering at the forefront, or was British engineering at the forefront of tunnel construction during the period that you've described? I mean, that's a sort of subjective, but nonetheless, what's your perspective on that? The extent to which we led the world, and the extent to which now, for example, those in Singapore or elsewhere are leading the world in engineering technology for tunnel boring.
So I think we were probably at the forefront of it until the mid 20th century. Maybe even through until about the 1970s with that early tunnel boring machine. Since then, there's been a huge amount of innovation coming out of Asia. There's some very innovative European companies such as Heron Knecht with the tunnel boring machines. But we still have a very vibrant tunneling industry. And so a lot of the techniques and so on, even if not the technology and the tooling, is being led in the UK. Okay, and I think we'll just briefly close out the remaining questions here, which are to say, there's a comment from Jordan Pedersen about staying with metal rather than redoing in concrete. I think that refers to your previous comments about the tunnel repairs. I believe you can see the remains of one of the tunnelling shields at the bank end of the Waterloo and City line. You can indeed. There are actually two tunnelling shields still in position. If you walk from the Waterloo and City line down towards the central line, the remains of the tunnelling shield are still in position, painted red with a plaque explaining what they are on the side of the tunnel. So that's really nice. The other one you can see is slightly harder. You have to book yourselves onto one of the Hidden London tours, or that are run by the London Transport Museum, of Moorgate Station, and at the south end of the Great Northern Railway, which is the one that's now part of Thameslink, not really part of the Underground, there is the remains of a tunnelling shield that was abandoned partway through the construction of a southward extension.
Very interesting indeed, thanks. And I think we'll just close then with a question about sustainability. The concept of sustainability is a relatively modern one, I think, by comparison with the timeline of your talk. But what sustainability measures are taken during tunnel construction? That's I think a question which relates more to the historical tunnel construction than nowadays. It's probably a bit unfair to ask you too much about modern techniques, but you mentioned the recycling of bentonite, for example, which of course reduces the cost and makes a lot of sense. Anything else that comes to your mind just before we close? I think probably the key one that sort of links in with what I've said is around the disposal of the clay. So rather than sticking it onto a barge and then just tipping it into the Thames estuary or into the North Sea at random and going, well, the sea will take care of it. If you look at things like the Elizabeth line, the clay there was taken out to build a new RSPB reserve at Wallasey Island. Yes. With the other recent ones like the Battersea extension, they've been used to remediate landfill sites. So the clay is all reused as much as possible there. Other than that, that's probably not my key area to be able to comment on. But good question, though. Thank you. Yes, very interesting. And of course, yes, Wallasey Island's a great example. Well, thank you very much, Tony. I'm glad to say that you've left a picture of your book on the screen, and you mentioned another book earlier on. Could you just remind us of that one, Tony? Yes. There's been quite a few. Building London Tubes is a sort of, it's not a new version. It's a follow-up almost to my previous book called Building the London Underground, and that was the full history all the way from the start of the subsurface tunnels of the Metropolitan Railway all the way through to Crossrail. So Building London Tubes has a lot more about more recent ones in it, but also tells a lot of the stories that I didn't have time to put into the previous book, and is a different format, so we can put the pictures, make the pictures larger and have more detailed captions explaining what's going on in them. Really, really great presentation, Tony. Thank you so much for joining us, and some really good questions as well in the chat. I'll just ask everybody to reach up and click on their react and little handy button there. That would be really great, and we'll draw this Lunch and Learn session to a close. So that's great. Well done, everyone. It's good to see. Thank you. Thank you very much for inviting me. It's been really nice meeting you all.